and I'm sure we will be able to follow. Okay, so
okay, I'll try and speak slowly and clearly, and we'll see how we get on. Okay, so well, thanks everybody. Well, first of all, thanks for inviting me here, Constanza, and delighted to be able to come along this afternoon to talk to you about this topic. Obviously, I think it's also a very important one. So just to kind of, by way of a kind of a roadmap, I'm going to talk a little bit very briefly. I guess you probably all know what I'm going to talk about, just to kind of clarify what I mean, what types of barriers I'm referring to in this talk, and then primarily really going to present some results from the EPA project that I was working on, wrapped up last year, well, wrapped up a couple of years ago, but the report came out last year. So looking at sediment connectivity, so looking at the impact of sediment, and then looking at channel change, at channel morphology in relation to a barrier removal. And then Constanza asked me if I could just briefly talk a little bit about barrier removal best practice. I'm not sure if I'm necessarily the best person to talk about that, but I'll give my thoughts on this from a hydromorphological perspective, and then also to touch upon kind of conversations that are being had around prioritization for barrier removal as well. So just in terms of the types of barriers, I guess what I'm not going to be talking about is large dams. We don't really have a lot of those in Ireland. So I'm focusing more on what we refer to as low-head dams, or sometimes run-of-the-river dams or structures. So there are really four main types. So we have on the top left here weirs, which we're all familiar with, and they all come in all different shapes and sizes. On the right-hand side here, this is known as a bridge apron. So it's associated with bridges. They're often artificial materials, and they're really designed to stop the river from cutting back underneath these bridges, so to provide some stability for the water flowing through bridge crossings, bridge spans. On bottom left, this is a culvert, and it effectively acts as a barrier because you get often a drop at the foot of the culvert, but also an increase in flow velocities and sometimes often very shallow water, which makes it very difficult. And of course, some sediment can't pass through that. And then on the right-hand side, this is a ford crossing. There aren't too many of these across the country, but they effectively are acting the same way or behaving in the same way as a weir. So in terms of the kind of broad effects, I thought I'd just bring in, I've just brought in a sort of a diagram here. This is from the Inland Fisheries Barriers website. It's originally, I think, from the US, and it kind of quite clearly or illustrates quite nicely the principles around the impacts that these structures have. So at the top, we have a free-flowing river. So materials can move down, sediments can move down, water can move down unimpeded, and in particular, fish can move upstream. So, and they've deliberately created this kind of undulating riverbed slope because that's the diversity, that's the complexity that you might expect in a natural flowing low-tick system. On the bottom here, we have a structure in place, so a barrier has been in place. In this case, it's a weir, and we can see more broadly the impacts. So first of all, the obvious impact is that you get this impoundment behind the structure. You've got deeper water there, more slower lentic flows, and sometimes as a result of that, you can get a change in the temperature. Sometimes dangerously warm water can be produced behind these structures, and you also get trapping of sediment behind these structures. So in principle, it's a little bit more difficult for the sediment to move across, and often this will ramp up, and that will also smother or bury the original substrate, the original riverbed. And then downstream of these structures, depending on their height, their slope, the depth and the velocity of the water moving over the structure, they become a barrier to fish that might be wanting to migrate upstream. So the hydromorphological impacts, I guess in summary, hydromorphology is a term actually that was really not that new, not that old. It's really come in with the Water Framework Directive in 2000. So it's a term that really kind of combines the hydrology, so the flows. So these structures locally alter the flows. So you go from free-flowing, faster, variable water depth, but relatively fast-flowing water to slow-flowing water, certainly upstream. And then they can also alter the sediment connectivity. So rivers are conveyor belts of water, but also of sediment. So it can impact the sediment connectivity. But you kind of put a question mark here because, I mean, that's something that hasn't really been significantly studied, certainly not up until about the last 5 or 6 years. And then there can also be morphological changes. So the morphology refers to the shape, the form of the river. And you can see just in terms of the slope of the bed, possibly in terms of the water depths, and sometimes in terms of the water width as well, you can see physical changes to the river. So what we did, what I want to present today really to you is primarily the results from a project that I was involved with that was recently kind of wrapped up and published by the Environmental Protection Agency with a funding body. We call it Reconnect, and it was really assessing the extent and impact of barriers on hydromorphology and on connectivity. And there were many sites and locations in this study, but I'm going to focus on 3 because this is really where the hydromorphological investigations were undertaken. Brownsbeck Brook, which is a second-order stream. It's a small stream. As the picture here, this is where that forward crossing image photograph comes from. And in this particular site, the barrier was removed. All 3 were supposed to be removed, but in the end, only 1 was removed. And I might mention a little bit on that later on in this talk. And then two studies where the barriers didn't come out, so we focused more on looking at the sediment connectivity, so looking at the sediment transport across these structures and the potential impact that these structures have on sediment conveyance. So with the sediment conveyance, so these 2 sites, one of them was on the River Duag in County Tipperary, and one of them was on the River Dalagan in County Waterford. We looked at both the bed sediment and we looked at the suspended sediment transport. So for the bed sediment, what we did, we used a fairly novel technique. We actually put little sensors in the gravel. So we went to the sites, we characterized the sites, and then we took out the gravels from the riverbed. When I say gravels, I'm talking about sort of particles that are somewhere between 30 millimeters in diameter, right up to kind of cobble-sized particles that may be of the order of 300 millimeters in diameter. And we drilled holes in them, and then we put these little tags in them. So they're known as radio frequency identification tags, and they are used in fishery studies to monitor fish movement. And we took them and put them in the sediment, and they have a unique identifier. We took them from upstream of the barrier, we took them from downstream of the barrier, and we also took them from control reaches, so unimpacted reaches further upstream of our site. 155 were seeded on the River Dalagan, and 138 were seeded on the Duag. And then we went back and found them, and it's a bit like taking a metal detector kind of type device, essentially sweeping the riverbed and trying to pick them up. And this is Colm Casserly, who was the PhD student who did the bulk of the work on this. This is part of Colm's PhD. So we found about 97% of them, and this is an image showing the movement of these traces. So the initial position of the traces in these yellow triangles, and you can see then the movement and direction of these traces on a subsequent visits. And what we found was that at both of the sites, the traces moved over the structure, including the largest gravel. So what we refer to as the D90, so the 90th percentile particle size was able to move over these structures. So it was such that it wasn't impeding the movement of even the coarsest material. But when we compared the transport distances and the transport rates upstream, downstream, and in our control reaches, we found that we had lower transport rates downstream. And we also had consistently coarser material downstream. So this indicates that there is some impact on the supply of the sediment over these structures. So although in the long term sediment is moving over, in the short term there is a disruption to the sediment transporting over these structures, and that is having an impact on particularly the grain size distribution, the pattern of grain size downstream, and therefore I guess potentially having an impact on habitat. Moving on to the suspended sediment story. So what we did here is we recorded suspended sediments coming into above our structures and then downstream of these structures. And we did this using a method whereby we don't actually record the suspended sediment. That's very, very challenging. We've had to take lots of samples. What we do is we monitor, we put in optical sensors that record the turbidity, so the cloudiness of the water. So you can see here, this is column checking a sensor in fairly high flows on the River Duag, and you can see the water is very brown, and that brown color is essentially sediment being transported in suspension. And we're interested in essentially what's coming in and what's going out, and we're trying to see if there is a difference, if there's any evidence of change in the inputs and outputs as a result of the structure. And so what we found was that we monitored continuously, but then we took the 31 best sets of data where there wasn't any kind of interruption or impact on the quality of the data. These sensors, so the sensors are kind of located in this kind of sort of set of devices here. Notoriously difficult to get good data because you get film building up on the sensors. Sometimes you get snagging of vegetation. Occasionally you can get infestations of invertebrates on there. So it's actually quite challenging to get good data. So we had 31 events where we had really clean data. And of those 31 events, 21 of these events showed an actually net increase in sediment flux downstream. So we've got sediment coming in, and then downstream in that same event, we've actually got more sediment than we would expect. And what we believe was happening there, and it's shown here just sort of schematically, is during these storm events, during these more extreme events, we're actually getting net export coming from behind the weir structure. So the weir structures themselves become a local source of fine sediment. And so although fine sediment is able to get over these structures, there is a modest impact on the amount of sediment that's coming downstream. And I guess potentially, if you've got large amounts of sediment coming from behind these structures during these storm events, a potential impact on sensitive biota downstream. So I guess the insights we got from the sediment connectivity investigations were that all particle size ranges can move over the barriers, but these barriers do continue to disrupt hydrosedimentary processes through this temporary storage and later release of materials. For coarse sediment, it's localized and it has an impact on the quality of physical habitat downstream, and which then kind of pinches out at a given condition, location downstream, and that will vary from barrier structure to barrier structure. For fine sediment, really what we might see is an amplification of sediment supply extremes downstream because of this sourcing of this locally fine sediment. And just as an aside, we also played around with putting one of these rather than having our tenor attached to column and him monitoring this on moving through the river and trying to identify the structures, we actually took the antenna off and set this up over a barrier structure itself. So we could actually record sediment moving over the structures in real time. So as the sediment moved over, it triggered the sensor and we were able to record it. And what was interesting here is, and this is another side, we could actually see as the flows increase, we start to see coarser and coarser materials moving over. So there's a strong link between the particle size and the energy of the river that the river needs to be able to move these structures, well, I guess, which is probably intuitive anyway. So that's, I guess, a summary, a brief synopsis of the sediment connectivity story. In terms of the morphological story and the barrier removal story, we were really only able to do this at one structure, as I said, which was this ford crossing at Brownsbeck Brook. So here the barrier structure came out during the study. And I guess from the point of view of understanding what's happening here, it's important to give a little bit of context to this site. So this is a second order stream. If you go back and look at the early historical Ordnance Survey maps, so you go back to the first and second edition Ordnance Survey maps, this stream actually was quite a sinuous channel. It was a meandering channel. So this is a trace of the channel back in 1910 from the second edition Ordnance Survey maps. But sometime between then and 1990, when we get the higher resolution aerial photography, we see that the channel has been straightened, and probably at that time the fourth crossing was put in. So you're dealing with a river that is already not particularly happy in the landscape. It doesn't want to go in a straight line. It actually wants to wiggle from side to side. So you're dealing with a river that's potentially prone to adjustment anyway, and then we have the barrier removed. And what we did is we monitored the plan form changes of the barrier by taking aerial photographs using a drone. And we also then conducted field surveys. So we monitored the long profile, and we also took measurements along designated cross sections to see how those would change over time. And we did this upstream of the structure, downstream of the structure, and we also then compared changes to a reference site. So, excuse me, what we call this a backsea study. So it's essentially a before impact, after impact, and also looking at the before and after period at a control site as well. So it allows us for some kind of reference, just in case there was a very extreme event and we might see changes in a control site as well. So just in terms of just in terms of the barrier removal, just to kind of to say how it was done. So this was essentially what happened was work was done by the Inland Fisheries Islands. So what they did was they blocked the Brownsbeck Brook just upstream of the barrier, and then they put in a bypass channel so that the water could flow around the structure. It's a fairly large structure, about 1.5 meters high and about 10 meters wide. They then removed the original full crossing. They installed, it's actually a culvert, but effectively the bottom part of the culvert, a box culvert, but the bottom half is buried. And so it effectively acts as a single span bridge. And once the structure was in place, they then backfilled the bypass channel and allowed water then to pass under the barrier. So we monitored before. We didn't monitor during the works, and then we monitored when the works were completed. And in terms of the results, I guess when we're looking at the plan form, we found no real indication of significant adjustment in our reference reach, and only minor bank erosion downstream. So most of the changes took place in the vicinity of the weir structure and upstream in our cross section. So what we see here, so this is an aerial photograph. This is where the structure was located, and then these are our cross sections. So U1 to U5 were 5 upstream cross sections above the barrier. And what we found was quite widespread bank erosion following the removal, particularly in the period between 2018 and 2020. So this was immediately after the period of the 2 years after the barrier was removed. There was quite significant bank erosion. So we had a sort of slab bank failure. We had a failure along fence lines, and you can see here further kind of large slabs of bank kind of collapsing in. And that continued for the following year as well. So quite significant changes in the channel width, and also quite significant amounts of sediment being released to the channel. So quite a lot of instability, despite the fact that the inland fisheries did their utmost to try to do this as carefully and as safely as possible. When we look at so that was the kind of plan for. When we look at the long section, so this is looking at the profile of the river. So this is the gradient of the river, including our control reach, which is located here, and then our upstream reach. This is where the barrier, the fore crossing, was located, and then we have these the reaches immediately downstream. The arrows give an indication of where our cross sections were, and you can see so the green and sorry, the yellow, the red and the blue line, shall I say, represent the profile of the river before the barrier was removed. So you can really see clearly here the sediment wedge that had built up behind the barrier structure. So all of this material here is essentially sediment. And you can see the change in the slope as well. So a much more gentle slope immediately upstream of the barrier structure. And then downstream, you can see the slope of the bed, slightly undulating, as you might expect in a river, but not a significant variation in gradient. And then following the barrier removal, so we did surveys in December 2019 and then in February 2021, you can see a marked difference in the gradient, and actually quite rapid return of the gradient to something not dissimilar from what you see downstream of the structure. So essentially all of this material has been removed. But very importantly, not a great deal of difference in the control reach. So some local slight changes to the riverbed, which you might expect when you've got an alluvial bed, but nothing of the order of magnitude that you're seeing where the barrier structure was. And that's very evident also in the cross section. So you can see these are the cross sections. So this is this location U2. This is U4. So this is the cross section in U4, and this is the cross section in U5. And as I said, the red and the blue lines represent the channel cross section before the barrier is removed, and you can see the marked difference in both channel width, representing the bank erosion, with rapid erosion occurring quite quickly and then slowing down in the subsequent couple of years, and also very importantly significant flow depth, channel incision, so channel lowering as well. And that channel lowering essentially migrated upstream and stopped just a little bit upstream of our U5. So the blue line here shows very little change in channel slope, channel depth, should I say, or indeed channel cross section in 2019 after the barrier is removed. But by 2021, you get this migration, this kind of cutting back of the river. And that cutting back of the river could have continued, but we found that it stopped at this location here. So there was a large riffle here. It was consistent in terms of the bed elevation, and it may well have been some bedrock, or it might have been some large glacially transported sediment. And what effectively that was acting as a kind of a controller to prevent any further migration of the channel bed beyond that particular point. So yeah, just to kind of point that out. I just wanted to make one final point here, and this is the reason why I included the photograph here. So during the course of this study, although we didn't see a great deal of sediment variation in the riverbed within our long profile, we did see clear evidence of sediment transport. So this is actually one of our sensors. So this is a sensor upstream, and during the monitoring period before the barrier is removed, that actually got smothered by sediment as it was moving downstream. So that illustrated to us that the bed was, although the bed level changes were reasonably stable, sediment was moving across the riverbed. So there was mobile sediment, so sediment was coming into the system, and that's bed sediment, and bed sediment was coming out as well. And that's quite important, I think, in terms of how this river has been able to adjust. Okay, so just in terms of the key findings, what we can say is that post-removal adjustment was controlled by the proximity to the barrier and also to bank erodibility. As you can see, there's very little riparian vegetation on here. The river was an unnatural position, so it was basically cut into former floodplain, and I guess the banks were quite susceptible to potential erosion. And that may well also have been exacerbated by this historical channelization, as I mentioned. Sediment throughput, as I just mentioned there, for replenishment and reorganization of the bed was very important. So as you can see here, you've got lots of sediment now, coarse sediment in the riverbed, and that's because the sediment was moving through and that was able to replenish and continue to do so. That's very important in terms of the sustainable functioning of this river. And what we found was changes was rapid, and it, certainly at the time of the termination of this project, ongoing. And what we also found that there was at that time no in-channel vegetation. So when we originally did this study, there was quite a lot of in-channel macrophyte vegetation, but that actually hadn't returned by the time we finished this project. But we are planning actually on going up there towards the end of this summer to do another survey. So we're interested in seeing if the rate of change is going to continue to reduce, and I would anticipate there might well be some in-channel macrophytes now starting to grow on the riverbed. We would hope there would be. And I guess that brings me to the last point, really, which is removal and post-removal monitoring is going to be important, and knowing the river beforehand as well, very important for restoration before you begin restoration works. Okay, so I wanted that was kind of Reconnect stuff, but I wanted just to kind of give a sort of perhaps a cautionary tale, what we could see would happen to a barrier when we don't remove it carefully, and it's removed in a more catastrophic fashion. So this is an event that occurred a few years ago on the Braemore River in County Offaly. And the Braemore, for those of you who are not familiar with this part of Ireland, is a tributary of the River Camcore, and it's a couple of kilometres downstream of Kinnity, the town of Kinnity. So this is a structure that was in disrepair and failed in 2018 during a storm event. So it catastrophically failed. It wasn't one that we were monitoring during the Reconnect project. We were doing the Reconnect project at that time, but it had been used, certainly from the hydromorphological side of things, but it was being used or was included as part of the invertebrate and fish studies. So we had some photos, not brilliant photos, But this was what it was like before the breach. So you can see the river bed here, relatively shallow on this particular day, but you can see a very clear layer of fine sediment in the impoundment. So the flow is from right to left, and the structure was a little bit further downstream. And this is a view looking downstream, so you can see this sort of lentic flows, fairly slow flowing water conditions upstream, and then this is kind of a reverse location, a view looking upstream. We then visited, or we were invited by the Inland Fisheries and by Offaly County Council just to come and have a look at this after the breach had taken place. So this is actually this structure, and this is essentially the hole that was left behind when this structure collapsed. You can see immediately you can see this coarse material upstream. What was particularly striking was the impact it had on the river banks. So prior to the barrier removal, there was relatively little riparian vegetation, as you can see, all the way along the left bank. On the right bank, you've got riparian vegetation, apart from just immediately upstream of the barrier structure. But the banks are reasonably stable. But during this particular event, I guess as a result of the rapid release of the water, the release of the sediment wedge, the change in pressure, and the hydraulic stress being exerted on the toe of the bank, these banks essentially collapsed en masse, and they were actually in some places reinforced by rock armor, as you can see, and all of that rock armor collapsed as well. So this was a significant problem for the landowner and for the inland fisheries, and there were also concerns for the road crossing. So the barrier structure is located here, and I guess the anticipated changes was that there's the risk of this changing in bed elevation, migrating upstream and impacting on the bridge as well. So I guess as a cautionary tale, it's probably, I guess, telling us that there is perhaps an elevated risk of allowing these structures to fail without some kind of input, some kind of controlled removal. And that will obviously vary depending on the barrier structure. But the challenge is, and it's interesting actually, because you sometimes hear conversations around, well, this barrier is on its way out. Well, let's let it fail. But clearly, this particular example anyway illustrates that might not necessarily be a good idea. And the challenge is that we don't always know how close a structure is to failure. There were conversations about the structure being in disrepair, but I don't think anybody expected it to collapse in the way it did. And I guess that leads me on then just to kind of a few more slides. I'm probably going a wee bit over time, but just in terms of barrier removal best practice. And I guess the first thing I would say, and I guess practitioners would say, is you need to know your catchment and you need to know your river. And when I'm thinking about the river, you also need to know what your river is like in that particular location. And you need to do that in terms of looking at the benefits. What are the benefits of the barrier removal, and also what are the risks? And from a hydromorphological perspective, I guess safely managing the trapped sediment is central, both in terms of the quantity, so how much sediment is building up behind these structures. This is the Dalagan where I showed you that picture before, but you can see clearly there's a huge amount of sediment that's built up behind this structure in the 40 or 50 years that it's been there. We need to know the size of the material. So if you've got coarse material, is it going to move more slowly? If you've got fine material, is it going to wash away more quickly, but potentially present a risk to sensitive aquatic species downstream? And one of the things certainly we've observed in looking at geomorphological studies of large sediment inputs to a river is often that tends to move en masse, and it'll move almost like a wave, a sediment wave, or sometimes referred to as a sediment slug downstream. So you might get this movement of sediment moving downstream. So where you've got large amounts of sediment, that can alter therefore water depths. It can alter, in extreme cases, can lead to changes in morphology as well, but can also then present a slightly higher risk to localized flooding because you haven't got the capacity where that sediment is building up. So I guess there are a number of kind of all sort of possibilities in terms of managing that. We can apply a more passive approach, so we can release the sediment more slowly. Some studies, some engineers will actually put sediment traps downstream and actually then control the release of the sediment, and maybe even sometimes remove the sediment from those traps. Or we can provide a more active approach, so removing the sediment. And that probably is more prevalent or more relevant where you've got issues of sediment quality as well. So if you're dealing with contaminated sediment. So contamination in industrialized areas might include heavy metals. I guess in Ireland it might include fine sediments that contain or hold a lot of nutrients, and including organic matter as well, which can present a risk to aquatic ecosystems downstream. So we need to consider the geomorphic stability at the site. We need to consider flood risks, as I've already mentioned, and I guess we also need to know our system downstream. What are the risks downstream? What are the sensitive species downstream? And when it comes to removal, I guess really it's the decision is based on a case-by-case basis, but where you've got smaller barriers, then single remove could be possible. But where you've got larger barriers, it really is much wiser to do this incrementally. So lowering the water level slowly, and in some cases it might not be appropriate to remove the barrier at all. And then you might look at some alternative strategies like modifying the structure, putting in some kind of grade control structure to allow fish passage. And very importantly, I guess, with all best practice is post-removal appraisal and monitoring. And I think we can learn from that as well. And that gives us insights into kind of future studies. So in terms of prioritizing removal, I mean, there's been so much on this now, and I'm not sure if this is necessarily so relevant to the audience here. But there's been quite a lot of work, both nationally and especially internationally at the European level, on sort of developing a decision tree, developing kind of criteria for removal. So we need to be thinking about the impact, the structure, in terms of the ecology, the sediment and the hydrology. We need to think about what the connectivity gains are, and that's really very much relevant to fish and opening up spawning grounds. A lot of decisions on barrier removal is related to its current use. Is it being used for anything? And if it's not, then is it obsolete? And removing it's not going to have an impact. Similarly with the age. Very importantly, the cost of removal. So barrier removal is expensive, and that's not just the physical removal of the structure, but it's all of the reports and risk assessments that have to be done in advance. And that was actually perhaps the most significant reason for why those two barrier structures weren't moved during the Reconnect project, because it just took so long to do the paperwork to get permission for these to be removed. And as part of that really is the institutional support. So in the case of the Dalagan barrier, for example, that had been built by a tile making company to provide water to a factory, but that factory had closed down. So nobody wanted to take ownership of that structure. And I guess there was a risk associated with removal of that structure, and it just became an impediment to it being removed. The timeline, obviously, how long it's going to take to remove and how long you're going to need to monitor it afterwards. And I guess perhaps less obvious are other constraints. We mentioned toxic sediments, but also invasive species. So barriers sometimes can actually act as a barrier for the propagation of invasive species. So that also needs to be considered when removing these structures. And then take all of these factors and then put some uncertainty on them as well, because that will have a bearing on the decision making. So if we're very uncertain about these bullet points, then that's obviously increasing the risk and challenges that might be presented when the barrier has been removed. So just to finish off, I was kind of curious and did a little bit of reading just in terms of the sort of state of play in Ireland in terms of barrier removal. And there's been a lot of literature actually now published on this. It's not an area that I particularly work in a great deal. But this recent report by the European Centre for River Restoration actually, it was really sort of a Q&A sort of exercise with all of the EU member states related to barrier removal, particularly in the context of increasing biodiversity and improving ecological function of our rivers. And I thought it was quite interesting in kind of towards the conclusions of this report where Ireland sits in all of this. So what they looked at was they looked at and they asked stakeholders in each of these countries in relation to what the drivers are for barrier removal and also what the kind of conflicting functions of these barriers are. And when they put those into a matrix, we see Ireland actually sitting right here, probably one of the perhaps the kind of the worst location in terms of having relatively few drivers for removal, but also having the barriers that are being targeted for removal also having many conflicting functions. It's not necessarily what's happening on the ground, but certainly it gives us a little bit of food for thought moving forward in terms of restoring continuity or continuity restoration in Ireland. you can see many other countries in Ireland seem to be in a far stronger position to restore continuity than Ireland, Portugal, Spain, and a few other countries that form part of this kind of little quadrant in this matrix. And on that point, I think I'll finish, and hopefully I haven't spent too long of the hour you have. Thanks very much. And I guess if you have any questions,